Okay, good morning, everyone. It's my pleasure to introduce you the speakers of our current seminar series on artificial intelligence. So today we have here Professor Juan Burguillo and also Elias Domingos. I will briefly introduce his based on their short bios, and then I will give the word to them. So Juan Burguillo received his master's degree in telecommunication engineering and PhD degree in telematics, both from the University of Vigo in Spain. He is currently an associate professor at the Department of Telematic Engineering and a researcher at the Atlantic Research Center in Telecom at the University of Vigo. He also received a medal for the Merit Order from the Ministry of Interior Affairs for supporting the Spanish security forces in the fight against childhood crime in the internet. He has directed and participated in several R&D projects in the areas of telematics and computer science in national and international calls. He has published more than 100 papers in international referred journals and conference proceedings, and also authored a book published by Springer Nature in 2018. He is a regular reviewer of several international conferences and journals, and he also the area editor of the Journal of Simulation Modeling Practice and Theory. His topics of interest include intelligent systems, evolutionary game theory, multi-agent systems, self-organization, and complex adaptive systems. So this is our first speaker. And also we have Elias Domingos, our second speaker, who received his master's degree in telecommunication engineering at the University of Vigo. In 2017, he was awarded the FWO Strategic Basic Research PhD Fellowship, which allowed him to pursue his PhD studies in the Vrije Universiteit Brussel, jointly with the University of Vigo. Currently, he is finishing his PhD degree, where he investigated collective dynamics in strategic situations affected by collective risk, such as the COVID-19 pandemics. And his topics of interest include evolutionary game theory, multi-agent systems, human-machine interactions, behavioral experiments, and intelligent systems. So again, it's my pleasure to have you both here. And now it's time to start our talk. I kindly ask the audience to, whenever you have questions, to use our Q&A panel on the right, and I will be moderating all the questions and providing the answers to them. Okay. So Juan, welcome again, and it's up to you now.
Thank you very much, Gabriel. It's a pleasure to be meeting. We'll comment some of our recent works, especially the ones related with PhD. So before that, I'm going to produce just a general speaking about the topic we are dealing with. So I'm going to share some slides that will introduce the topic of agent-based computing for game theory models. And basically what we're going to deal in this introduction are the topics of complexity, the links between complexity and game theory. And then I will exemplify an example, which is the classical iterated prisoner's dilemma, which is a common topic for game theory, where cooperation and defection are common issues in these areas in order to model social or economic interactions, for instance. So time ago, as you have said, I published a book with several co-authors, and we are going to deal with topics which are in this book in chapters 2, chapter 3 about complex networks that I'm going to introduce, chapter 5 about multi-agent systems, and then chapter 7 about game theory. It was a pleasure, in fact, that together with Gabriel and Anna Bazan, we three collaborated in writing a chapter for this book, which was Coalition of Electrical Vehicles in the Smart Grid, which has been strongly cited. I mean, the works we have done about that topic. So what is what we are going to deal with here in this talk? So mainly we have a complex system that is an entity composed of several parts which are interconnected, and that the collective behavior of those parts, that could be, for instance, agents or any kind of element which is interacting with many others, make more than the sum of the individual components. So basically, if we see this picture, complexity deals with computation, adaptive behavior, complex systems, and also chaos and fractals, which we are not going to deal with, but which are pretty, let's say, common topics and popular in areas like physics, which has also a strong connection with complexity. So those collective behaviors that we are going to see appear as the interaction of several parts, and we call emergent those behaviors that are not codified on any of the parts, but that appear afterwards. So dealing with this topic is the idea of a complex network, which is strongly related with social networks that we all know, and social networks is a subset of possible complex networks with some kind of topology. So let's say that a complex network is a structure which is made by connected nodes. So here the nodes are connected with links, okay? And the color in this picture is basically depending on the number of links a node has. So these nodes may represent individuals, groups, or organizations which are linked with the others. For instance, a network of people which are working together and have relations with other people in that network. So those relations may be friendship, like in Facebook, economic deals, internet connections, like in any kind of, let's say, communication network, neuron connections, protein interactions, etc. Anything we want to describe using such kind of network. And typically in this network, as I said before, we have several links for a node. So that will be the degree of a node. It means the number of links it has connecting itself with the other nodes in the system. So for instance, we could have non-isolated nodes. This is a way to describe it, a degree distribution, where on the axis, in the x-axis, we have the degree, the number of connections the node has, and in the y-axis, we have the number of nodes that have such number of connections. For instance, we have here with degree 5, 8 nodes. It means that 8 nodes has 5 connections. And with degree 9, we have in this particular graphic 3 nodes. Okay, all nodes are connected in this graphic, and I will come back to this at the end of the talk when I will introduce a simulator. So there are several types of networks. The most simple ones are regular or structured networks. Here we have a link where every node, a network where every node has 6 links with the adjacent ones. Here we have another one with 4 links per node, classical lattice connection in square style. Okay, but we also can have much more complex networks. So it was a classical work where you can start from a regular network. You can see here in this ring where every node is exactly connected with 4 other nodes. You see that there are 4 links for this node, and also this has also 4 nodes in the external part of the circle, and it happens to all of them. Okay, so starting with this type of regular network, I'm modifying one link. For instance, we can break this link here and select another network, another node in the network to connect with. So for instance, this node breaks one of its links, this one, and connects randomly with any other. For instance, with this one, same happens with this node that has another connection with this. And following this procedure and connecting nodes and increasing the probability that any link is connected, we can move from a regular network like this, where we have the randomness 0, to a random network where we have perhaps a random value of 1, which means that for every link we are reconnecting itself, and we could obtain something like this random network here. Okay, and in between we have something which is called small world networks, which are pretty interesting because of their properties. We are not using here a random value of 0, neither a random value of 1, but we are using some value in between, typically 0.1, 0.2. So these small world networks have a shortest path length, which means that we can connect typically from any node to any other node in the network in a few number of jumps. It means traversing a few number of links to reach any other part of the network. And that is very an interesting property, which in fact happens in the internet, but in many of the social networks we are facing nowadays on the internet. So this is a key property, that these networks can be traversed by a small number of links, and they are also high clustered. It means that the nodes are connected strongly among them, creating some groups, but still having the property to move from any part of the network to any other very simply. So small world networks, together with the regular ones that appear here, are pretty popular, but there is also another kind of network which is really popular, and they are scale-free networks. And the scale-free networks contain set of nodes that have a high number of connections. They are highly connected hubs, and that also provides some particular properties to those networks. So you have the same picture, the same graphic we saw before here with the degree distribution, but instead of having the count of the number of nodes having just the value, but instead of that using the logarithm, we could have some interesting properties. As you may see here, in the axis we have the degree, and here we have a fraction of nodes. And using logarithms, we can find that a few nodes have very high number of connections, like 1,000 in this case. Even some nodes only have perhaps 1 or 2 connections, like those 2 1 nodes here. So with this property, we have a kind of network where nodes have higher connectivity, a few ones, but most of the others have lower one. And this is very common in networks like social networks, like for instance Facebook. And the topic of influencers, for instance, deals with that. It means a few people that have a very high number of followers, while most of the people have about 200, 300, 1,000. But let's say that influencers could have something like million of connections or followers, so they are behaving something like a scale-free network. As a difference with the previous one, these networks are low clustered, and remember that in small world networks we have high clustering. Okay, so this kind of networks compose the way that our agents or our elements like coalitions, groups, or whatever are interacting. So when they are connected using those kind of networks, we have a complex network, and we have potentially a complex adaptive system. And what does this mean? Well, complex because of the network connections, for instance, adapting because let's say that the agents that are participating in that network have short-term actions and perhaps long-term strategies which are changing depending on the context. And of course, systems where we can, because of their strategies and interactions, we can see macro patterns that emerge from that. For instance, how the birds flew when they go together from one place to another to avoid predators. So this is the complex part of my talk, the initial talk, and we are going to deal now with evolutionary game theory. This discipline from game theory was introduced mainly to describe the interactions and to modelize species in ecological environments. So basically, EGT models the application of interaction between different strategies which are used by populations along generations, let's say, in an ecological system. As a difference with classical game theory, participants here do not possess unfailing Bayesian rationality. It means that they play such kind of game, let's say, such kind of interaction with their limited resources, as we all do in our real life, okay? So players learn by trial and error, incorporate what they learn in their future behavior, and die or somehow change, let's say that adapt, that is the complex adaptive system part, if they do not. So there are several ways to describe infinite populations or finite populations. We are going to deal with finite populations in the rest of this talk, and mainly in the other one, which is even smaller populations. And for instance, in smaller populations, we have here the generations. So at time 0, we have a certain population, and then we start to introduce or mutate some of the strategies. We have here a D, which means the factor. We will see afterwards what is related to. But we also have a C, which means cooperating. So it means like a population where agents can be defecting the others, let's say non-cooperating with the others, or cooperating with them. And along time and evolving those generations and modifying the number of agents depending on their payoff or how successful they are in the population, we can change a population at this time that could be, at this generation, that could be mainly composed by cooperators and only one defector, and in the last generation we only have cooperators in the end. So this is mainly what we are going to deal with in this first talk. Let's say a population of agents that are connected between them using some kind of complex network, and they are going to play some kind of game, and they are going to evolve in order to see what strategy is much more popular or much more interesting or much more successful when playing. So those agents can play using different strategies, different roles. They could be fixed agents that use, for instance, static strategies, like always play cooperation or always play defecting. It can be some kind of strategies coming from game theory, like tit for tat, Pavlov, or any other. They can do mimetics, like imitation. You do what the others do, like in fashion, for instance, sometimes, or how people get dressed. Or they could be reactive learners using some kind of, let's say, reinforcement learning strategy in order to learn from the past and their self-experiences. That could be learning automata, quality learning, difference learning, and many other strategies you want to include here, for instance, neural networks or deep learning or whatever. So our agents are going to use these strategies, and we want to use also EGT, evolutionary game theory, to see which is more successful in that kind of scenario. So this kind of approach, this type of approach has been very popular in economics, for instance. So there is an area in economics which is agent-based computational economics, ACE, which is the link, or is, let's say, the intersection about, among many other disciplines, like, for instance, computational intelligence, computational economics, mainstream economics, behavioral economics, cognitive psychology, and of course, intelligent agents, and all together compose agent-based computational economic models. We are going to see today some interactions among some of these disciplines, especially intelligent agents, behavioral economics, cognitive psychology, and how, let's say, users, or real humans, interact playing some kind of game. And finally, I'm going to introduce in the last part of this talk the prisoner's dilemma, which is a classic game, in order to exemplify what I'm describing here. So basically, the prisoner's dilemma is a game where we have two players that have two options: to cooperate with the other player or to defeat. The other player has the same options, and depending on what they do, they have a payoff. So the first letter is the payoff for agent I here, the second letter is the payoff for agent J here. And so if they both play CC, they will get the same payoff, which is R. and I won't describe what these letters mean now, but there is a matrix rules in order to have the prisoner's dilemma game. So we are going to pass directly to the classical matrix, which is used for this game. So these are the typical values for the prisoner's dilemma game matrix. So if both cooperate, they receive 3 points each. If agent I cooperates, gets 0 points. If agent J defects, while he gets 5 points. Okay. Vice versa, if agent I defeats, it gets 5 points, while the other one gets 0. And finally, if both agents defeat each other, they get 1 point each. So if we look at the matrix, we see that for agent I, it is much better to play defect, because in this case he wins 5 instead of 3, and in this case he wins 1 instead of 0. So independently of what the other agent J does, it is better for him to have D as the strategy. As they are complementary and we have the same situation in the other side, same happens for agent J, playing D is better than C, gets 5 instead of 3 and 1 instead of 0. So the strategy DD is the rational one playing this game only one time. But the interesting thing in this kind of game, if we play it many times. So for that, instead we play with all the agents in the system, we are going to use a two-dimensional square lattice, like this one. It means a regular network. And we can simulate how the agents are, how successful they are, depending on what strategy they play. So we have n agents interacting one by one. In this case, the green agents interact with the central one. Okay, we have a von Neumann neighborhood, only neighborhood with 4 agents in green playing with this, but we can increase the neighborhood, for instance, to accommodate the yellow agents, and in this case we will have 12 agents, or just the ones in the square round, which will be 8. It doesn't matter, it can depend on what or how big the neighborhoods we want to play. So we can do that with a neighborhood value. Okay, so I'm going to show you, in this part simulator. I need to change now the environment. By the way, Gabriel, you are receiving everything without noise? Everything is fine? Meanwhile, I stop sharing that?
Yeah, it's fine. Everything is going well. Okay. Okay, so
now to share global desktop, and probably you are seeing a set of squares in the middle of the screen, plus we have let's say 2 extra windows here, graphical windows. So we are seeing lattice network with 2,500 agents, and they are going to use some kind of basic strats to play the prisoner's dilemma. Okay, so depending on the strategy they are using, they have different colors. And when I play run, each agent is going to play 50 times with the surrounding 4 agents. Okay, so this is an agent, for instance, which has a kind of a strategy which is all C, and it has 4 networks, as you may see here. Okay, so in this network, we are using 4-degree distribution because all the nodes are connected with the closer 4 ones. Okay, so we have 4 connections per node and 2,500 agents with that particular degree. So I go for run, and what we see here is some kind of probabilities for deciding the action to play in the next round. But what you are seeing is that at this time the network is evolving and the agents are deciding what strategy to play in the next generation, depending on how successful they have been in the past. Okay, so these probabilities that appear here means that a kind of strategy that means first start cooperating, and if you receive a defect, always defect, is the most successful one. This strategy is called spiteful and is the one in yellow. I will show one of the node. This is a C spiteful, which means that it starts with C and then follows that strategy. Okay, so what we are seeing here is a run for this kind of environment where the agents play the iterated prisoner's dilemma, among them some kind of tournament, and we see that within this particular conditions, the more successful strategy is becoming the spiteful one because it's getting all over the network. Even though some other strategies can survive, like this one, for instance, which is a Pavlov strategy. Well, sorry, this is a TFT strategy, but we can modify the conditions of our network. And for instance, instead of having a spatial network, we can take a scale-free network, as I said before. You see the same because you see all the nodes and their strategies, and we can see how they evolve here. But now if we take a look at the node degree, we see that they follow such kind of degree connection where we have, for instance, 42 nodes with which are much more than 20 links, while most of the nodes, in fact, mainly half of them, have only 2 links. Okay, so they are playing again the same game, but now the connections among them and the neighborhoods are different, and you see how, for instance, in this case, the spiteful strategy has become much more faster to go over the whole environment because the connections, let's say, that allow it to get over there. So this is a kind of model to describe how strategies can be successful or not, depending on the connections. And this is the introduction to the second talk, because Elias is going to show you some kind of game, the CDR, who will describe the characteristics of that game. And in this case, the participants he's going to use are mainly 6, and they are playing, it will be something like one of those clusters, but we can consider to extend his game to situations like this. It means to have a lot of clusters interacting among them and having something like spatial connections among the clusters, or small world connections, or scale-free network connections, and so on. So he will go on to describe, he will go on to describe you that part. I'm going to go back to myself and the presentation, just a minute. Okay, so so here we are, and as I said, that mainly ends my presentation. I have some extra slides, but just to comment that the Prisoner's Dilemma is a very interesting game from the game theory point of view, because as I said before, this is the rational outcome when you play it once, but as you have seen, when you play it many more times, it becomes the iterated version of the Prisoner's Dilemma. Then it gets very interesting properties, and a lot of works and a lot of books has been related to describe such game. So, okay, I receive a message that you are not seeing this slide. Sorry, just a minute. Is it now? I guess yes. Gabriel, you can tell me by audio.
Yes, now we can see.
Okay, so anyway, I was just describing this last slide where you can see again the matrix, and the Nash equilibrium for this game, but it's a very interesting game because, as I said, defecting is the dominant strategy, DD is the only Nash equilibrium, but at the same time, any other option is much interesting for the agents. So all the others are something we call Pareto optimal. So from the game theory point of view, this is a dilemma because this is the natural and rational outcome for playing ones, but the other ones are much better. So that's why it's called a dilemma for the players. But as I said, interacting over the game many times with the same players can avoid this Nash equilibrium in the one-shot play and go for some extra situations where other strategies where cooperation is much important can be playing a role. And anyway, thank you for your attention, and if you have any question for this part, I will be glad to answer it. Of course, continuing with Elias' presentation.
Okay, so thank you very much, Juan. I'm not sure what's better, if we should have the questions here or later, but I do have a personal question here, and it would be useful maybe for the audience also. In your simulation, it was not clear to me what strategies were the best there, because it seems that the frequency of cooperate and cooperate was having higher frequency than defect and defect, right? Was that just my impression, or was that really the outcome of the simulation?
First of all, you are seeing now the simulator?
Not yet.
Not yet, okay. Just a minute. Because it seems that when I change, I guess you do now, right?
Yeah.
Okay, so those different colors describe different strategies. As you can see, the most popular one is the orange color, which means C spiteful. It's a kind of a strategy that starts cooperating, but as soon as they get a defect, they defect all the time, never stopping. Okay, but we will go, for instance, for this blue one, which is CTFT, which means that they do what the opponent did. It does what the opponent did in the previous round. So it's mainly a cooperating strategy. And we have the green ones, which are Pavlov strategies, which is somehow like humans behave. Like if I go right, if I am winning, I continue with my strategy. If I start losing, I change it. So it will be, it doesn't matter if you were doing defecting or cooperating, you go for that. And as you can see here, the most popular one is spiteful, which is half cooperating strategy somehow, but starts cooperating here. And the second more popular could be perhaps TFT and then Pavlov. But there are many other possible strategies. They are described by these probabilities here, but I don't want to enter into those details. Some of the strategies are somehow have a name. But in this case, we can see that under these particular conditions, cooperating is much more popular than defecting as a general issue. But changing the conditions, changing the networks, changing the payoffs of the matrix, you can get different results. And how many of the works are in the way to describe how these strategies are much better or wrong, depending on the conditions they are playing with.
Okay, interesting. And in the end, I'm not sure if Elias is going to talk about this, but as the agents evolve their behavior by interacting with the others, are we somehow going to converge to a situation where everyone is going to cooperate, right? That's the idea.
In this case, not necessarily, even though in general the idea is to modify the games in a way where people really cooperate. Somehow you have to define the rules to avoid defection. You can translate or create a metaphor to pass from this simple abstracting game to what people do in real life, like for instance paying taxes or behaving well with others and so on. So the idea here is on how to create a game where it is much more, let's say, successful for the game itself to behave cooperating, but it means that for every agent has to be also more interesting to go and to play that way instead of playing defecting. Elias, in fact, will deal with that over a climate risk dilemma, where we have to deal with some kind of public good game, and we have to try to get everybody cooperating in order to really pass the risks linked with that dilemma.
Okay, so thank you very much again. Maybe it's now we should go with start with Elias, and if we have additional questions in the end, please this is something to the audience. Please write your questions on the Q&A panel to the right, and I will be moderating them to ask them in the end to our speakers. Okay, so thank you again, Juan. And now it's time to Elias start speaking. And Elias, it's now with you.
Hi. Okay, so again, I'm Elias. Are you able to see my presentation?
Yes, just a minute. I just received a question here to Juan, probably. So I will just ask that question before Elias starts, sorry. So the question is, I was wondering whether affective states can be used to improve the strategies since they are important in human cooperation. Are you aware of works that have considered affective states, such as emotions and personality traits, to improve the strategies?
I can also answer that. I can answer that if you want.
Yeah, go ahead, please.
Okay, Elias, if you want to go, please.
Yeah, there are particular papers of Kathleen Jonkers from Delft, University of Delft, have dealt with this. There are, I think, papers, those are using other sorts of models, so learning models, in the iterated prisoner's dilemma. But I think, I don't remember the name of the authors now, but I think there's also some papers that use affective states in evolutionary models. But the objective is not to improve cooperation, but rather to understand why we have cooperation. Because as Juan said, the prisoner's dilemma is an excellent model of what happens in society. If you only act individual, searching for your individual interests, then you should defect. But collectively, we are all better cooperating, and in fact, we do see cooperation in society. So why does cooperation appear in society? And we know that people have emotions. We know that society has moral structures, and so all these different factors we can add to the prisoner's dilemma. Also, if we are doing mechanism design, we can try to change the game, adding new rules so that cooperation can emerge. And this is another type of study.
Okay, thank you very much. We have also a suggestion here of literature, which is saying that Bazin and Bordini in 2001 used the OCC model of emotions. Okay, this is related to the previous question. Okay, thank you for the questions and thank you for the answers also. So Elias, it's now the word is with you.
Okay, thank you, Gabriel. So thank you, Juan, for the presentation. In his presentation, Juan was basically giving you some tools, some excellent tools to model and to study, and also to search for new ways, as Gabriel was saying, in which we can increase cooperation in social situations. But I'm going to focus here in my presentation more on modeling and particular social scenarios. In concrete, we're going to look at scenarios of collective risk. And what I'm going to do is I'm going to show you two types of models. One is the evolutionary game theory that Juan has presented, and another model in which agents adapt by learning through interactions with the environment. And I'm going to show you also some experimental results with humans. So we get humans in a laboratory and we ask them to play some kind of game. And this gives us some data and allows us to study what happens in these social scenarios. And actually what you see there in the figure, this figure, there is some kind of joke about the climate change and politics relating to that. Politics, instead of taking action immediately, they will only investigate what happens when we are all underwater. And in fact, climate change is a type of collective risk scenario. But to understand a bit more what actually is collective risk, let's take a recent example. So the coronavirus pandemic. This coronavirus pandemic exemplifies two of the main properties of a social dilemma. One is this immediate and individual level dilemma in which people are going to, so individually I am going to comply to the COVID measures. In some countries they have confined people in their houses. I'm going to comply to these measures if I perceive the risk of getting sick to be very high, right? So young people actually may forfeit this. They think they're not going to get sick, so they go out. But there is a secondary dilemma that spans through time, and it's related to this figure that you see there. That if these young people go out, then the number of cases of sick people will increase. The virus will spread much faster, and we'll have this first curve that has a much higher peak. And what will happen in this case, in comparison to the second curve, is the health system may collapse. And if the health system collapses, even if I'm not going to get sick of COVID or die, if I have a car accident, I may not have place in the hospital. So it increases my risk of death in a different way. And this affects everyone. And that's what we call collective risk. And so what we do to study this from our game theoretical perspective is to make a simplified and abstracted model of what a collective risk situation is. So I'm going to show you what is what's called the collective risk dilemma. So basically, we get a group of people. Here you see 5. In our experiments, there are 6. And we give them a fixed initial endowment. And then we ask them to contribute to a common pot throughout a certain number of rounds, 0, 2, or 4 of this endowment throughout the rounds. So when contributing, they are taking out their own money and giving it to the common pot. And at the end, what happens is that if you surpass a certain level of contributions, then everything is good. And you keep whatever you didn't contribute. So what you see there is that not everyone ends up with the same payoff. This means that some people contributed more than others. And this is already part of the dilemma. We want to keep as much as possible, but at the same time, if we do not avoid the disaster, then we may enter in this other situation that there is a certain risk that there is going to be a disaster, that everyone is going to lose all their wealth, all their accumulated money. And we want to avoid that. And this is where the dilemma is placed. And actually, this situation is even more complex because there are other uncertainties that may affect it. There is this risk that we already talked about. We don't know what is the probability that a catastrophic event may occur. And even if we know this event might not be certain, it might not be the event might not happen with 100% certainty. Maybe there are 50% chances that let's say climate change happens. This is not a good example because climate change will happen if we don't do anything. But what people do in these cases, we don't know. We also may not know what is the threshold of contributions that we need to surpass. In the case of climate change, for instance, we don't know exactly how much we need to reduce the CO2 emissions. And we need to understand whether this affects people behavior or not. And the last one is time. What happens if we don't know what is exactly the amount of time we have to avoid this disaster? In the case of climate change, do we still have 10, 50 years? How much do we actually have? and this actually might produce big changes in behavior. So let's focus on this last type of uncertainty just for now, because we have performed some behavior experiments with people, and we have seen something very interesting, and that when you have timing uncertainty with respect to with when you don't have, people act in a reciprocal manner, meaning that they tend to only contribute if others are contributing as well. Now, this may be seem trivial, but actually, if you look at the results, here what you're seeing is that in the x-axis, we see what the group has contributed, and the y-axis what a player contributes on average with respect to it. So this basically means that if the curve is in this direction, can you see my mouse or not? Okay, if the curve is in this direction, participants are mostly compensating. Here.
Yes, we can see your pointer there. Sorry.
So if the line is in this direction, participants are mostly compensating, meaning that they are giving more when others are giving less. And when it's in this direction, participants are being reciprocal. They are giving more only when the others are also giving more. So it seems that here we can see also the proportion of actions, and maybe it's even easier to see. It seems that when we have timing uncertainty, just by having it, we suddenly have this burst in reciprocity. And we need to find some kind of explanation for it. And this is where evolutionary theory is very handy, because it allows us to fully characterize the dynamics of a certain collective system. And so I'm going to show here as a very simple model that we've created for that situation, this particular situation that I just showed, in which we only have 5 strategies that represent what we saw in the experiments. I'm not showing all the experimental data just to be a bit fast. So we choose these 5 strategies. We have people that contributed less, here represented by this all 0 strategy that contributes nothing. People that contributed mostly on average 2 at each round, and here represented by this all 2 strategy. People that contributed 4, and then the compensators and reciprocals. And when we plug this on evolutionary theory model for finite populations that Juan has showed you before, we are able to construct this type of image that basically represents a Markov chain, where the lines, so the arrows pointing from one strategy to another, indicate some kind of dominance relationship. This basically means that in this case that you have an arrow going from reciprocal to all 2, the all 2 strategy is actually dominating the reciprocal strategy. So if these 2 play against each other, all 2 will evolutionarily prevail. And what we see here is that the main difference between not having timing uncertainty and having timing uncertainty is that when there's no timing uncertainty, all 2 strategies dominant. It's not invaded by any other strategy. Whilst when there's high timing uncertainty, it is actually being dominated by all 0. And this is basically what is changing dynamics. And because of this, you actually create some kind of cyclic dynamics that increase the level of reciprocals in the system. And this is very interesting because even this very simplistic model allows us to explain this characteristic of our experimental results. The problem of this type of models, however, is that if we want to increase the strategic space, so explore what happens if we have more strategies in the system, it can become very computationally costly. It can become computationally hard. So what we are going to do is we're going to use another type of model in which agents learn and adapt by interacting with their environment. And this will allow us to explore the full space of behaviors without having this drawback of this strong computational cost. Of course, in the secondary model, we are not able to fully characterize the system, but I'll show you that we are able to reproduce experimental results in the same way. So before anything, let me show what the other experiments on the type of other types of uncertainty have shown. In this left figure, you see experiments with only impact uncertainty, so only risk. And what we see here in the yellow boxes is that only when the risk is quite high, so 90%, do participants actually start to contribute. And the y-axis here, we're showing the success, the fraction of successful groups, and in the x-axis, the risk. However, some other researchers, that's what you see here in the blue bars, have also checked what happens if we add another feature to the game, which is communication. If participants before the game starts are allowed to say what they are willing to contribute. And what it shows is that if you add communication, it actually increases a lot the success for 50% and 100% of risk. In the 100% of risk, they reach full success. The red bar is basically our experiment that reproduces the yellow bar, and we have a slightly higher success, but the difference is not significant. And what we see in the timing uncertainty experiments, the one that we performed, is that if the timing uncertainty is low, there's almost no change in group success. So it remains almost the same. But if we increase timing uncertainty, it actually decreases. So it seems that there's some kind of unlinear relationship. And with respect to threshold uncertainty, that they did the experiments with communication, you see that even though there is communication, there's a drastic decrease in success. So it seems that not knowing exactly what you have to contribute, even if the uncertainty is small, completely destroys cooperation. And at the same time, it seems that building a communication system that is effective and robust is not simple, because it can be affected by these types of uncertainty. So now I'm going to introduce you the model that we've used. So in figure A, what you see is how the agent interacts with the environment. It's a normal reinforcement learning model. The agent observes the environment, makes an action, and then observes what happens. So observes the next state of the environment and receives some kind of reward or payoff. But actually, in our case, the environment, and that's figure B, is composed not only by the game that is being played, but also by all the other agents. So actually what we have is that we have a population of agents that start by being very similar, and then they are sampled randomly into different groups of size n to play the collective risk dilemma. And then afterwards, with what they received, what they accumulate some wealth, and then they update their strategy based on this wealth. And then the population changes in the next generation. And the agents may not be the same anymore. They start to become different, and we start to see what the strategies will actually dominate or prevail in the population. And again, we repeat the same process. And what we observe is that given this type of model, we actually see the same that we saw in the experiments. For lower level of risk, actually until 0.5, there's almost no cooperation. And afterwards, we enter in some kind of transitory period. And when risk is high, cooperation is almost 100%. This is this first figure. We can also see what happens when we introduce uncertainty. So threshold uncertainty, as we've seen here, the parameter delta simply indicates the level of threshold uncertainty. The higher the delta is, the higher the threshold uncertainty. So we see that it definitely affects the cooperation for high risks. It completely decreases. But at the same time, for lower risks, it seems to increase cooperation. The reason for that is that this uncertainty about the threshold means that the threshold can also be smaller, and that's why you're seeing this increase here. In the case of timing uncertainty, we don't see this, and we see that it does affect success as well. But as we had seen in the experiment, the success is almost not affected for lower levels of timing uncertainty, that's represented by the parameter W. And it starts to be affected for higher values of timing uncertainty. But even more interesting is that this population of agents, we can actually look at what is the strategy that each of these agents have developed, and what are the differences between these strategies. So what you're seeing here in this figure is some kind of lower dimensional plot. So we simplify the dimensions of the strategies into two, just to be able to see some clusters in the behavior. And we color this by the different clusters, and each symbol represents that they have learning under one type of uncertainty. And the interesting thing is that the agents that have learned under timing uncertainty seem to be quite separated from all the other agents. The agents that have learned under threshold and impact uncertainty are quite mixed in the population when we do this kind of representation. But these ones are different. And even more interestingly is that if we look at what is the behavior that the agents have learned for these two clusters that appear under time and uncertainty, is precisely a reciprocal behavior. They actually learn to give less when the others are given less, and more when the others are given more. So we see that the same behavior that we had observed in the experiments that we analyzed through evolutionary game theory also emerges in these other type of models. And so now, just to conclude, what we see is that we can use different types of models to study social dynamics. They can give us different insights. In the case of EGT, they are very interesting because they allow us to fully characterize the dynamics of the system, to know which strategy is dominant and which isn't. But sometimes they can become very computationally complex. So we can use this other type of models, this population-based learning models, to explore the full strategic space. We also see that uncertainty is very important for collective dynamics, and it can completely change the behavior of human participants. And that reciprocal behaviors emerge under time and uncertainty. So that's it. This is just to show the people that were involved in this work. So we have Francisco Santos, Yelena, Georg, Juan, who presented before. Tom Leonard is also my supervisor. And that's all. If you have any questions, this is my contact in Twitter. That's all. Thanks.
Okay, Elias, thank you very much for the talk. Both talks were very interesting, and they shed light on some of these important aspects of game theory and how they impact the real world, right? And this is very important. Okay, so we are still waiting for the questions, but I do have a few questions, of course. And one of the first things that I was wondering is, because in your case, Elias, you also use human participants in your experiments, right?
Yeah.
So a question I have is that, okay, so rationality is a kind of assumption that we usually make in the game theory literature. And in practice, you know, this is not something that humans really present in practice, right? So what's the role, or maybe what's the impact of the lack of rationality in humans in your experiments? How do they affect the dynamics of the thing?
Okay, that's an interesting question. Thank you, Gabriel. For those, I guess everyone knows what is rationality, but it's simply a general assumption in game theory to say that each agent, each person is trying to maximize their own payoff, and this is their only objective. The payoff or utility may be composed of different things, so this will include different objectives. And this is a simplification assumption. It really enables to simplify the math, but not always it's included in traditional game theory. They also you have utility theory and beliefs that can be used to not, if you don't want to make the assumption of rationality, but the models become much more complex. In the case of experiments, obviously what has been observed in many different experiments is that people don't tend to abide for this rationality behavior. One example, even though a bit controversial, is another type of game that we didn't mention called the dictator game. That is not really a game because it's not truly strategic. That's why it's a little bit controversial. You simply have two players. One of them is the dictator and another is a receiver. And you give some money to the dictator and you ask the dictator to share this money with the receiver. The receiver has nothing to do, does nothing. The dictator can decide everything. So if you're acting rationally, the dictator should give nothing because the receiver is not going to do anything. But if you put two people in a laboratory, then you start seeing that this doesn't happen and people actually share a non-zero amount with the other. And this doesn't make sense. And this is just an example of the situation. It happens in many other situations, including my game in this collectivist dilemma. When the risk is very high in collectivist dilemmas, the rational thing to do is to simply contribute exactly what you need to contribute, and achieve the target, because the payoff or the expected payoff that you would receive otherwise is much smaller. But you see that people don't do that. And actually, when you look at the post-experiment questionnaires, you have participants that say, well, I stopped contributing because I got mad at this other guy. They don't know who each other is. It's completely anonymous, but they say, I got mad at this other person because he or she wasn't contributing from the beginning of the game. Even though he started contributing afterwards, I cannot forgive. And this is not rational. According to the rationality assumption, this doesn't happen. So we cannot model this taking this kind of assumptions.
If I can also comment something about it, that is also very common about the assumptions usually applied in traditional economics, where they consider that humans are rational players and they are getting a lot of information and dealing with that in order to take decisions. But we know that in reality it doesn't happen like that. And the typical issue about describing that is that humans are conditional cooperators. It means that they cooperate if they think like they are going to get some payoff or utility from that, but altruistic punishers, that when they are somehow irritated or retaliated or so, they start to punish the other, even if they are not getting the right payoff they could get. So that also links with the question sent before about emotions and how humans behave. And there is a whole area in economics which is behavioral economics. We were dealing with that also in our work because one of the co-authors is an economist. And in that area, they study precisely how humans behave in traditional economic games or in real economic games in order to try to describe that.
Right. So, if the audience wants further information about this we just discussed, I'm putting here small reference, which is very interesting. It's about the nature of human altruism, which is quite old, but it's very interesting. And if you want additional information, please take a look there. Thank you for the answers. We have also another question here, which is a more general one. And the question is, modeling social interactions with multi-agent systems is a kind of simulation, right? What are the main methods of evaluation for this kind of simulation? How a researcher can show that a specific multi-agent simulation is a good and realistic simulation of a determined situation, or that a model of, or that a model is better than another one? Okay, these are several questions. If you want to read them, you can take a look on the Q&A panel to the right.
Yeah,
I can read it for you.
So then let Elias also to contribute. And that is a very good question about how to validate models. And there is a long tradition about discussing how to deal with it. In my opinion, this is really difficult to do. I mean, first that be sure that your model describes reality, and also that the results of your model can be applied and also could be considered as a prediction of reality, as in classical sciences for predicting what is going to happen, like it happens, for instance, in physics or many others. However, it is very good. I mean, I think that simulations are very good in order to test the validity of some models. I mean, if you consider that a model is true or it's assumed like a dogma, and then you use a simulation and you play that model and you see that the results are not going like they should be, considering the classical dogma, that could be a way to somehow study what are the problems with that dogma and to produce modifications or start new future work in order to deal with that. That has been applied many times in economics about many issues that were considered something like assumptions in classical economics, and that nowadays they are under the pressure of changing those ideas and create much more complex models, many of them using simulation, in fact, because we are dealing with complex adaptive systems that are not easy to describe with classical mathematical tools, and where simulation comes into a really strong tool. Elias, if you want to add something.
Yeah, so one thing is that we do experiments with people. We have experimental data, and that's how we validate models results. Other is that in general evolutionary, depending on the model of evolutionary game theory that you're using, but in general, if you go for infinite populations, you're using replicator dynamic, which is a differential equation that fully characterizes the system. So it's not really a simulation. You describe the whole dynamics of the system. In finite populations, you can use a Moron process. That's the chain, the Markov chain that we see in my image, and that Juan showed to you, that also fully characterize the system. Because of that, it is numerically hard. The time complexity of a memory that you will need to fully create a transition matrix for all of this growth with the population size and the number of strategies, even more than an exponential. If I remember correctly, it's a binomial. So then, of course, you need to go to other types of methods. We use Monte Carlo methods to be able to identify stationary distributions that will tell us what is the amount of time that the system would spend on average on each state, or at least on the main states. Or we can have this simplification assumptions. For example, if we say that in the case of evolutionary game theory, the probability that a strategy will change randomly into each other, that's called mutation probability, is very, very small, almost tending to zero, then the system simplifies. The number of states is basically the number of strategies. And then we can just do this mathematically. Otherwise, simulations provide a very good tool, but of course, we always need ways to be able to validate them or understand that they are going in the correct direction. Okay. And in the case of reinforcement learning, it is a bit more difficult to find out whether the simulation is actually showing what's happening in reality. But for that, we have experimental data, and we have this more simplified evolutionary game theoretic models that allow us to know whether things are going correct or not.
Okay, excellent. Still on the same topic, it would be interesting if you, okay, so for those that don't know, Elias and Juan, they have a lot of experience with on designing experiments with humans. I know that some of you may be interested on this kind of validation and experimental settings. So could you please give some advice to students who want to perform some experiments with humans? What kind of thing should they be aware of before they start? I know this is something far from easy, right? I remember that when I was, on my postdoc there at UB, you, Elias, spent a lot of time just designing the experiments and then collecting data and then inviting a lot of people to participate, which is not trivial also, because even though you were giving some, on that experiments at least, giving some money feedback, reward for them. So how do you, I mean, what are the first steps you would suggest?
Okay, so experiment-wise, it really depends the type of experiment that you're doing. In experimental economics, you have some rules that you have to abide to, which is first you need to guarantee there is completely anonymity between participants, and second is that there has to be an incentive for them to act rationally, or at least to want to play the game. There is some other rules, but those are the main two. This incentive is normally monetary. It can be there can be other types of incentives, but commonly it's monetary, and so we have to spend quite some money paying participants, and this money depends on how they do. It's not a fixed amount. Depending on what they do during the experiment, they get more or less, like as if they were playing in a tournament. But the main thing in general for general experiments is the design. You need to have a good design from the beginning to make sure that you're measuring exactly what you're measuring. And even then, often things that you didn't expect appear. Sometimes your hypotheses are not validated, and you get negative results. Fortunately, that wasn't my case. But if this happens, the problem is that in the literature, they are not very happy about negative results. It's quite difficult. Now it's changing, but it's quite difficult to publish. So imagine you spend 2-3 years of your life doing research in something and you get negative results, and what do you do?
Yeah.
Indeed, what Elias did was first to start with the experiments with real humans, and then to create the model with PBL, considering those strategies that were abstracted and presented in here in the slides. But it was really interesting because he was able also to describe experiments that have been done before in the literature. So it was pretty interesting, and I think that the model that he has developed could be useful in order to test and predict experiments under scenarios that have not been seen yet, and also to test them afterwards to see if it really happens like we hope. He has a lot of experience dealing with humans. Mainly I was dealing with simulation in the past, so he is the right guy for behavioral issues.
Yeah, excellent. By the way, if you, I mean, now I'm talking to the audience, if you are interested in any of the topics they discussed, please get in contact with them, because we have collaborations. I mean, we started collaborations, but we are still, out of time to really proceed with them. But if you are interested, you can reach us to look for possible, works to do with us. Okay. I have a few more questions, but maybe this is the last one, just to avoid consuming all your time. I know that Juan, you have something to do later, so I don't want to waste all your time. So in this final question, I would like to ask you about other potential applications of this kind of research you are doing. So would you consider other scenarios like traffic or smart grids, or anything else that might interest the audience or even us here?
I will start a bit and let Elias, who has a lot of probably examples of situations where his model and the situation related with the collective risk dilemma could be applied. However, there is an area in game theory which is, sorry, that's my dog.
Is he okay?
So there is an area of game theory which is game design, where you try to design the games in a way that the players will go for the cooperating or altruist behavior, avoiding defecting the others, just because it is much more useful for them to behave like that. There are some kind of techniques or tools like, for instance, punishment, like we have in real life for people that behave wrong, or let's say using somehow trust, reputation. Those are techniques that are extra, that have been also studied along the last 20 or 30 years, a lot in the area of multi-agent systems, norms also. So there is a lot of examples and real life scenarios where you can use these techniques, use these simulations, and use evolutionary game theory to get a hint about how the real situation is, and then try to explore potential tools in order to have more cooperation than you have at the present. Elias, please.
Okay, thank you. Yeah, I agree. Also, I mean, in general, well, evolutionary game theory and game theory are the same thing. It's just that game theory provides a different type of tool so that we can sometimes more easily study some other types of problems, normally biological problems, using computers. As one has said, there's other mechanisms that appear that can be studied through game theory, such as trust and social norms. And particular social norms are quite interesting because when we study human societies, apart from our biological needs, there's also culture, and this leads to certain norms that have been created, and this has led us to be able to cooperate. But now our society is changing, right? We are interacting more and more with artificial entities. For the internet, we are, when I call, at least in Spain, any travel company, the first one that I hear is a chatbot. And even in certain online services, you are sold things by a chatbot, or you enter Twitter and suddenly you receive some news, and this news is recommended by some kind of artificial agent. The question is that we don't have yet, or we are starting to build social norms to interact with these agents. We don't know what is actually the effect that this is going to have on our societies. And in theory has a direct application towards this kind of things. It's the perfect tool to study how a system of trust and norms can be built or should be built with artificial agents, so that we don't break cooperation in our society, and or we avoid fake news from spreading, and which sometimes have catastrophic effects. Yeah.
Okay, excellent. So mechanism design is probably one of the things that might be interesting here, right?
Mm.
Okay, excellent. Okay, so I believe we do not have any further questions here. So thank you again for the excellent talks you both gave today. I hope you enjoyed talking with us today. And also, you're more than welcome to visit us at some point. If at some occasion you can come to Brazil, just let me know, because you'll be more than welcome to come here, visit us, know how things work here, our students, and everything else. Okay.
Thank you, guys.
So Elias, thank you again. Juan, thank you again. Have a nice day there, and I hope to see you soon.
Thanks a lot.
Same for you.
Thank you for the invitation. I'm glad to continue our cooperation with you and your colleagues.
Okay. Thank you very much.
Thank you. Bye.
See you.